Welcome to this online course on steam and condensate system. This first section is intended to give a brief non-technical overview of the steam plant. It offers an overall explanation of how the different parts of the steam plant relate to each other, and provides useful information for anyone who is unfamiliar with the topic, prior to progressing to the next sections and before undertaking any form of detailed study of steam theory or steam plant equipment. So please take the time to watch this section carefully, and feel free to ask us for help in the Q&A section or drop us an email at contact@wrtraining.org. Thank you again for enrolling in our course. Take a look at the following simplified 3D animation. The boiler that you can see here is the heart of the steam system. In a boiler, heat is added to water to convert it to steam at high pressure. The boiler comprises of a water and steam side and a flue gas side. The typical modern boiler is powered by a burner, which sends heat into the boiler tubes. As shown now on screen, the hot gases from the burner pass backwards and forwards up to 3 times through a series of tubes to gain the maximum transfer of heat through the tube surfaces to the surrounding boiler water. Once the water reaches saturation temperature, the temperature at which it will boil at that pressure, bubbles of steam are produced, which rise to the water surface and burst. The steam is released into the space above, ready to enter the steam system. The stop or crown valve isolates the boiler and its steam pressure from the process or plant. If steam is pressurized, it will occupy less space. Steam boilers are usually operated under pressure, so that more steam can be produced by a smaller boiler and transferred to the point of fuse using small diameter piping system. When needed, the steam pressure is reduced at the point of fuse. Now, as long as the amount of steam being produced in the boiler is as great as that leaving the boiler will remain pressurized. The burner will operate to maintain the correct pressure. This also maintains the correct steam temperature, because the pressure and temperature of saturated steam are directly related, and this will be explained in detail further ahead. Lastly, keep in mind the boiler has a number of fittings and controls to ensure that it operates safely, economically, efficiently, and at a consistent pressure. This will also be explained in detail further ahead. The following figure depicts a simplified steam boiler process. Here, the quality of water which is supplied into the boiler is important. It must be at the correct temperature, usually around 80 degrees Celsius. This is done to avoid thermal shock to the boiler and to keep it operating efficiently. The water must also be of the correct quality to avoid damage to the boiler. Ordinary untreated potable water is not entirely suitable for boilers and can quickly cause them to foam and scale up. The boiler would become less efficient and the steam produced would become dirty and wet. The life of the boiler would also be reduced. The water must therefore be treated with chemicals to reduce the impurities it contains. It is important to note here that both feed water treatment and heating take place in the feed tank, which is usually situated high enough above the boiler. The feed pump, highlighted now on screen, will add water to the boiler when required. Heating the water in the feed tank also reduces the amount of dissolved oxygen in it. This is important as oxygenated water is corrosive. Now, at this stage, don't worry if the points highlighted here are not clear for you. We will get back to them and demystify them and discuss them in exquisite detail in later videos. Welcome to this online course on steam and condensate system. This first section is intended to give a brief non-technical overview of the steam plant. It offers an overall explanation of how the different parts of the steam plant relate to each other, and provides useful information for anyone who is unfamiliar with the topic, prior to progressing to the next sections and before undertaking any form of detailed study of steam theory or steam plant equipment. So please take the time to watch this section carefully, and feel free to ask us for help in the Q&A section or drop us an email at contact@wrtraining.org. Thank you again for enrolling in our course. The following figure depicts the upper half of a boiler with the piping system conveying steam to the point of use. This piping system represents a typical configuration of a steam reducing station, including a control valve and a condensate trap set. These will be discussed in detail in a later section. Now, if the water level inside the boiler were not carefully controlled, the consequences could be catastrophic. If the water level drops too low and the boiler tubes are exposed, the boiler tubes could overheat and fail, causing an explosion. If, however, the water level becomes too high, as highlighted here, water could enter the steam system and upset the downstream process. The result would be wet steam. For this reason, automatic level controls are used. The following figures depict two examples of level control system used for a steam boiler. The left-hand system is an on-off control. The right-hand system is a continuing modulating control. Boiler controls and control theory will be explained in a later section. For now, keep in mind to comply with legal requirements, level control systems also incorporate alarm functions which will operate to shut down the boiler and alert attention if there is a problem with the water level. A common method of level control is to use probes or sensors, as seen here, which sense the level of water in the boiler. At a certain level, a controller will send a signal to a control valve or a feed pump which will operate to restore the water level, switching off when a predetermined level is reached. The probe will incorporate levels at which the pump is switched on and off, and at which low or high level alarms are activated. A typical example is now shown on screen for the purpose of illustration. Now, it is important to note here that for steam boiler safe operation, it is a legal requirement in most countries to have two independent low-level alarm systems. Chemical dosing of the boiler feed water will lead to the presence of suspended solids in the boiler. These will inevitably collect in the bottom of the boiler in the form of sludge and are removed by a process known as bottom blowdown. This can be done manually. The boiler operator will open the blowdown valve for a set period of time, usually twice a day. Other impurities remain in the boiler water after treatment in the form of dissolved solids. Their concentration will increase as the boiler produces steam, and consequently the boiler needs to be regularly purged of some of its contents to reduce the concentration. This is called control of total dissolved solids, or simply TDS control. This process can be carried out by an automatic system, which uses either a probe inside the boiler or a small sensor chamber containing a sample of boiler water to measure the TDS level in the boiler. Once the TDS level reaches a set point, a controller signals the blowdown valve to open for a set period of time. The lost water is replaced by feed water with a lower TDS concentration. Consequently, the overall boiler TDS is reduced.